Joseph Poon. Joseph, of course. Joseph, of course, is one of the co-inventors of the Lightning Network and is also running a new blockchain, which he's going to tell us about. So, Joseph, all yours.
Thanks, Dan. So, as a show of hands, how many people were here yesterday? So I don't want to be too redundant. Oh, great, not that many. So I can just repeat the same slides. I'll put in some new stuff, but okay. So how many people have a general idea of how it works, or like read the paper descriptions? Okay, about 30%. Okay, cool. So as a background, I think it's important to sort of understand and reason about the motivations behind Plasma. So as we all know, the security of blockchains are derived from everybody validating what you see on the blockchain and not trusting what other people tell you. So your code verifies what you receive, the blocks you receive, and the information you receive to ensure that all the data is correct, because there's no single trusted authority of the correctness. And that essentially creates upper bounds in the amount of computation that you can do, because logically, if you need to verify, for example, all the financial transactions in the world on chain, that creates a lot of expense. And this is especially true and magnified for computation. If we want to be able to compute complex contracts, then everyone else would hypothetically have to compute these complex contracts. So there's a lot of emerging work with channels and other technologies to be able to reduce the amount of computation necessary to be able to do that. And if the blockchain is sort of the ground truth of the world, then we should minimize the amount of truths being asserted to it. And you really don't want to disagree about this ground truth, because if you disagree about this ground truth, then the system sort of breaks down. It's sort of like if you had sort of like two Supreme Courts that disagreed with each other, and you sort of didn't know which to build case law upon, then you can't really build some system which we can be able to reason about and build contracts around. And on a technical level, that means that state synchronization across the participants becomes imperative. You have to enforce the current state. With global data, it's easy because everybody has access to the current state. Everyone receives the blocks, everyone analyzes this and processes the same blocks, and therefore you all have the same set of data. When you don't have global data, then that issue becomes a little bit more complicated, and is going to be sort of the central theme of a lot of the work around scalability. It's sort of the other side of the coin when it comes to reasoning about scalability. And in this case, withdrawals is sort of a misnomer, but it's sort of when you're moving funds or moving the state between the different chains, that becomes essentially you're saying, okay, we have this global state, we're pre-committing some amount of funds to it, and this is true for any channel type construction. You're pre-committing funds to it, and when you pre-commit funds inside, you have local agreement between two participants on who has what within that fund, right? So if you had 1 ETH and you're splitting it up 0.6, 0.4 between you and some other person, and then update it to 0.5, 0.5, in order to move forward, you both need to have sufficient data. In this case, the data is the other person signing off on the new state. If you don't have access to the data, then you can't prove the current state, and that becomes a huge problem. And in this case, it's resolved just by forcing hard synchronicity between two parties. Hard over time. Eventual synchronicity between two participants, whereby when you move to the next stage, both parties have both signatures, each other's signatures, and at that point you sort of, okay, you have the data available. Using this construction becomes increasingly complex, forcing synchronicity across all participants, because when you have complex contracts, that means that you're going to have a lot of participants who may not be online at the same time and may not be able to compute all of the data at the exact same time. This creates constraints around, liveness, whereby, liveness is basically everybody has to be online. And it creates incentive towards halting the system. So if you have, some computation between 10 parties, then if like 3 of the parties stop computing or signing off on things, then they can sort of halt the system very easily. So you sort of face this challenge whereby you choose either greater robustness around keeping the system operational versus security. Additionally, you want to minimize the amount of ledger entries on the chain. But really, the data availability problem permeates all of this. So what is Plasma? I'm going to run through this a little bit shorter compared to the presentation yesterday. You can watch it online if you want to see a little bit more in depth, but I want to give more time towards reasoning about the economic models and these sort of use cases for this. So Plasma is a construction of blockchains in blockchains. So you have some blockchain, and then you have some which spawns a child blockchain, which can spawn further child blockchains, and that's sort of how you reach scalability. And it's functionally a set of smart contracts that runs on the blockchain above it, or in the root blockchain actually, which everything else derives from its security from. And this smart contract effectively defines the consensus rules of the child blockchain as the form of fraud proofs. So you're not actually directly running the blockchain on the root blockchain, in this case Ethereum. You're only actually computing things in the event of disagreements about matching consensus. So if you violate the consensus rules, a proof is given on the root chain, and that block gets rolled back. And we'll go into that in a second. And by constructing things in a set of nested chains, in order to do computation across these nested chains, you have to reason about this in a different way because you're dealing with many different systems. So the standard way to deal with disparate systems is to use something called MapReduce. So MapReduce is functionally when you split up the work, you have a map function, and when you combine the work, there's a reduce function. So that's a way to distribute work and sort of understand the result from many different computers. Plasma is compatible with on-chain scaling solutions such as sharding, various block size constructions. So essentially, if you have better capacity on the root chain, that should be able to increase the robustness of Plasma as well. So if you increase the root chain, gives you some X factor, Plasma can run on that and give you a further Y factor, and above that you can run channel construction such as Lightning. So when it comes to the design goals of Plasma is to show that it's possible that the blockchain can encompass a huge part of the world's global transactions. Not just financial transactions, we're also talking about computation in general. I think it's really going to be possible to put a lot of, data storage, computation, web services, all of that on the blockchain, and I think it's technically feasible to do so, even with the technology we have today. We just need to write the code, and then it'll get done. Post Metropolis, no further changes are necessary on Ethereum. And this can get you, payment and ledger scalability. Ledger scalability is an interesting one because, if Vitalik says, a blockchain, one of the key components of a blockchain is, the data storage component, and you have computation on that storage. Well, you don't want to have too much data storage on the root blockchain, otherwise it becomes a little bit cumbersome for anyone doing full computation. So this can give you scalability on, the state as well. So what does Plasma really look like? It's really just a set of libraries, and you add on some business logic. So this business logic can really be anything. You can, by default, let's say you have a payments chain as like the default, and then you wanted to add on some social network like CRUD components to it, and you can do so. And suddenly now it's a social network chain. You just write the code, upload the smart contract onto Ethereum, and then now you have some social network, and as long as you design the economic incentives correctly, it'll perpetuate and exist. And the operators of that chain are economically incentivized to run it. You can create, decentralized applications such as a decentralized exchange, or you can run, your own private blockchain running on top of a public network. So this construction allows you to create applications which you and a set of participants are able to verify and enforce on the root chain. If you don't care about the results, if you don't care about the computation, let's say you're not using the social network decentralized application, you don't really need to look at it at all. You're not really computing much at all. You're only computing very, very small commitments on the root chain. And that creates great efficiency for not only people using the system, but also everyone else on the network, because they sort of don't need to pay attention and they don't need to really look at it at all. That's just a bigger picture. So what type of data is committed on the root chain in most circumstances, in nearly every circumstance? In this case, do I have access to a mouse? Oh, fantastic, I do. Can you guys see that? Oh, great. So when you have periodic commitments to the root chain, when you create a new block in the child block, in this plasma block number 1, there's some transactions that occur inside, there's some state inside, and they commit a hash of that block, and it's signed by the block creator, and it gets submitted to the root chain. And the root chain and everyone else running Ethereum doesn't really do anything with it. You just the data's stored, it's okay, whatever. Because the data isn't actually stored on the root chain when it comes to, let's say there's 1 ETH in this plasma block, it's just 1 ETH is just stored in the contract. There's no accounting of who actually owns it. It's accounted inside the plasma block itself, and it's only when it's either withdrawn or disputed that there is enforcement of correctness. And in this case, enforcement of correctness is the most important when it comes to withdrawals, because, and this is a bigger picture of that. So essentially, let me backtrack a little bit. Alice, when she holds funds inside this plasma block, and the only thing being submitted is, let's say, 100 bytes or 200 or so. And in this block can possibly have millions of transactions in a single block, and ideally not millions, let's say hundreds of thousands, but you can get net millions. And you only submit 100 bytes, and it's enforceable. And we'll see later how it's enforceable. So here's the issue, right? If only a small amount of data is being submitted to the root chain, what happens when there's an invalid state transition? After all, Alice, the creator of the next block could say, well, it's not Alice's money anymore, it's Mallory's. And I'm friends with Mallory, so I want the money too, and Mallory's giving me a cut. So because this data isn't on the root chain, what happens then, right? Well, in this case, if you're Alice and you have block data number 4 available, block number 4 data available, what happens is that you can submit a proof on the root chain, because a smart contract in Plasma is going to allow you to submit proof that block number 4 is invalid, and as a result, block number 4 gets rolled back. So this is sort of what happens there. Before, it looked like there was going to be block number 4, but anyone that has observed block number 4 can submit a proof on the root chain, which includes, Merkle proof that, this was included in block number 4, and then perhaps the transaction itself, which, let's say didn't have a correct signature. And then everyone on the Ethereum network processes that and says, oh yeah, this didn't have a correct signature, and the smart contract said it must have a correct signature. So then what happens is block number 4 gets rolled back. The creator of block number 4 gets heavily penalized. So because of this penalty, you're going to be economically disincentivized from propagating invalid blocks. But here's the problem. Let's say, and here's a fundamental problem around, when you're dealing with interactions between multiple blockchains and want to move funds between multiple blockchains, is that in order to prove fraud, you must have access to the data. Remember earlier I was talking about how data availability was sort of the fundamental problem that we're thinking about. And the reason for that is because with fraud proofs, you need this block data, and what the attacker can easily do is submit the block hash, sign it, and not tell anyone. And after a while, they can attempt to withdraw your money because the withdrawal proofs will look legitimate and no one else will be able to prove fraud. So what you do is you pre-construct the design so that if you are not able to receive the block after any blocks after some set of time, you can withdraw your funds. So the interesting thing is you can't actually prove on chain whether data is withheld or not easily. It's sort of like a he said, she said situation, because it could be a situation where it's like, okay, Alice is like, well, I didn't get the block data. And let's say Bob is the block creator and Bob says, well, I gave Alice the block. There's no way to really prove that via a very, very expensive interactive process, and which basically requires dumping the block on the blockchain. So that's sort of always been this weird wrinkle in designing these systems. So what Plasma does, and the solution in my view for these types of situations, is you pre-design it so that you can exit during some time window, where during this time window, if you haven't spent the money, and it creates this challenge game, if you haven't spent the money, you're going to be able to exit. And by broadcasting a transaction on its parent. So this is sort of a bigger picture, and the idea is that, let's say Alice only has access to block number 3, she doesn't have access to block number 4, and is suspicious and concerned that there's a state transition here where, let's say Alice sends her money to someone else, and she doesn't have access to this block data, and therefore is unable to prove fraud. She submits an exit on the root chain, whereby she says, I'm going to exit from this blockchain, and has to wait some time period in order for that exit to be fulfilled. However, that requires Alice to be able to have space to submit the transaction onto the chain. So in order to make that economically efficient, what we could do is construct it instead as a nested set of trees with possibly disparate sets of participants. So it's possible whereby there's this first tree depth, this is Bob, and this is run by Carol, and this is run by Dave. If you're Alice and any one of these fails, you just go to the other ones in order to, juggle your position around. And in this case, this is sort of the example of that, whereby if this one fails, the one in red, you broadcast on the first tree depth, and then you move onto the second tree depth. And that way, the transaction doesn't get broadcast on the root chain. Of course, if all of these 3 fail, you thereby do need to broadcast on the root chain, and provided that there is block availability. The fun part about this is that if you hold funds on, let's say, this third tree depth in blue, you only need to watch its parents, because its parents are the ones enforcing your state. And if, let's say, the second tree depth submits some invalid state transition, you're able to prove fraud on its parents. But essentially, if the other ones in gray don't affect you directly, you don't need to watch the chain. So this can create significant efficiencies when it comes to scaling up on the validation and light client side. So if you're a client, you can do possibly full node validation of the first, second, and third tree depth because you're not actually having that many state transitions. You could imagine this nesting out to thousands of different blockchains, and you only need to worry about the state transitions, perhaps, which is happening, maybe there's only hundreds of transactions occurring per day, and there's only commitments occurring periodically to its parents. So as a result, you're probably only processing data in perhaps the tens of megabytes in order to, whereas the entire network itself is processing, many, many, many gigabytes or terabytes of data. Because we are constructing things in chains, like I said earlier, you may want to be able to do computation between these states. And MapReduce is, a pretty standard construction. There's a lot of literature on it. There's a lot of literature talking about how to do different things like sorting, like various, basic computing algorithms, whereby you can just use that and plug it in, plug the algorithms in and use it to be able to reach scale on blockchains. The only difference in this case is that we are Merkleizing the commitments of the states before and after of the state transition in order to make proofs of the state transition. So it's basically provable MapReduce in a certain way. That way, compact provable. That way, when you send work to a child chain, in a map function, you are committing to the data being sent to the child chain. And then when you do the reduce function, you are also committing to the end state of that to the parent chain. And this allows you to reach scalability and be able to reason about how to delegate work across these different blockchains. So when it comes to future work, there's future work on mechanism improvements, so creating more incentive for operators to incentivize correct exits, minimizing block withholding attack incentives, so more mechanisms around that. Right now, the mechanisms are fairly robust so that if you as an individual are able to get your money out, provided that there's block space. However, you want to minimize the incentive for the operator to attack the system, even if you as an individual are able to get your money out. And one way to enforce this is if recursive snarks or starks exists, then basically you just punt the problem away. But ideally, I strongly believe in defense in depth. And ideally, you want the system working robustly with just an open system with like very simple math. So one can reason about in the long term how people reason about blockchain security. The first line of defense could end up being hardware security modules, whereby you just say, okay, if you're a block node operator, you have some HSM, but I don't want to rely on HSMs because I strongly believe in open source and they kind of suck because they sort of create centralizing effects when it comes in because there's strong network effects around that. The second line of defense could be something like ZK snarks or starks, and then the third line of defense could just be an open mechanism game between the blockchain, whereby you can submit data in time for disputes and stuff like that, which is sort of the core design of Plasma. Ideally, you have the system work with just that component, and the other ones are just a convenience. So additionally, there's additional research necessary for token incentives, especially token incentives between the child chains, and additional aspects related to hybrid proof of authority, proof of stake constructions. So what does this get us? I believe I think it's interesting because I think it creates a way to reason about the sort of future of blockchain scalability, and it sort of rhymes with the way our society works today. We sort of have a court system, and if you view the blockchain as an adjudication layer, the highest mode child chain is sort of like the district court or the local court, and then its parents are sort of like the court of appeals, whereby if your district court messes up, you can sort of like go above to its parents. And if the court of appeals messes up, well, you go to the Supreme Court. In this case, Ethereum or the root blockchain is the Supreme Court. It's sort of the source of ground truth. And that's sort of where you submit, your smart contracts. That's where, everything is sort of like, that's the true consensus layer. But you don't want to clog up the true consensus layer. You don't want every court case going to the Supreme Court. That doesn't really work. It's just a couple old guys, you don't want to like, they're old enough already. You don't want them doing too much work. So that's sort of what, like taking that analogy, you don't want everyone in the world computing it, like my computer doesn't want to do that, right? It's a little bit old too. Oh, that means I'm going over time. Okay, let's just run through this. You already read it. So what I really want to talk about is like what this means when it comes to proof of stake economic incentives on the second layer. In this case, we're talking about Bob creating all the blocks, right? But you can also do something where a lot of people create the blocks, or a set of participants create the blocks. You know, instead of Bob, it could be Bob, Carol, Dave creates the blocks, and they each take turns, or they can do, you know, some type of majority construction. You know, there's a lot of different there's a lot of different distributed systems literature on how to split up the work. The fun part is, because this is a second layer, you can sort of punt on the problem. Because things like creating timestamping, you just like, okay, the parent chain does, the root chain does the timestamping, Ethereum does the timestamping, so you sort of like punt that problem away. So actually proof of stake on the system becomes really, really easy in comparison. But on the other hand, the constructions you design on top of here may not be applicable for, you know, proof of stake on the root chain, which the Ethereum Foundation is doing like amazing research on. So what's interesting is that you can, this is fully compatible with a lot of, you know, new models, new economic models when it comes to tokenization. Currently, a lot of people talk about use tokens, you know, like you buy a token in order to, you know, use some functional thing on the blockchain. This is more closely aligned with proof of stake tokens. So it's similar to like, you know, using some type of token on some root chain, you know, ETH or something like that. Eventually, if you can do ETH, bond your ETH and do proof of stake on that, then you can get some return for holding ETH. And then to reason about it with, you know, the gas stuff, it makes a lot of sense. So what you could do is you could be paying ETH fees for the transactions on the root chain and the disputes on the root chain. But the transactions going on inside this plasma chain, the person that gets to create the blocks are the token holders. So what happens is that it's a proof of stake of the token holders. So you issue some ERC20. And by issuing some ERC20, the owners of that have a right on a proportional share to be able to generate blocks. And the person that generates blocks, of course, collects transaction fees. So there's an economic incentive to be able to, you know, collect transaction fees and to run the blocks. And what's interesting is that, you know, you have a situation which is not the similar dealings of the principal agent problem that we have with securities, right? With securities, you're delegating trust to another party to act on your behalf. And because you're delegating trust, you know, you sort of, you know, like you sort of have to trust them to be able to operate correctly. You know, will the CEO, you know, operate my company and not just like take all the money, right? In this case, you are directly taking action on the system. So by having a specific stake, you know, let's say you own like 5% of the coins, you can create 5% of the blocks or collect 5% of the fees. If you take action which is incorrect, you get penalized. If you take action which is correct, or your, you know, transaction selection algorithm is better than another, you can collect more fees. So it's a different construction than what we deal with today in society. But, you know, by owning perhaps a portion of, you know, the tokens, you can construct a model whereby you're creating a decentralized network that nobody really has full control over, right? Imagine if you created a social network on top of this. You've created, you know, let's say a Reddit clone or something like that. You write the smart contract code, upload it onto Ethereum, and then issue some tokens. And it's the token holders, and assume the tokens are widely distributed among society. Well, it's the token holders creating blocks, and they're going to keep creating blocks, right? Because like they're economically incentivized to collect transaction fees. Who really owns this system at this point, right? It's very similar to like who really owns Ethereum, who really owns Bitcoin. Well, I mean, I guess it's the token holders, but like, you know, the guy who like uploaded the smart contract code, he can't like if he said like, yo guys, let's shut this down, the token holder is going to be like, no, right? Like if Vitalik was like, hey, Ethereum's done, like how about we just like close up, everyone's going to be like, no, we're keeping this running, right? So like it's going to be a different dynamic that could exist. And as a result, you're sort of removing the trust in trusted institutions to be able to operate on your behalf. And this is sort of like a new model that can exist. on top of Ethereum that has significant scalability. And there's some use cases.
Cool. All right. Cool. Great. Thanks. Thanks,
Thank
Joseph.
you. Sorry for running over time.
Why don't we take one question while Vitalik gets set up? Yes, please. Back.
So, can you compare and contrast this with some of the other consensus algorithms? Like I think DPoS is probably very close to what you're trying to do in plasma.
This is completely unrelated. So the question is, how does this? Oh, sorry. Yeah, the question is, how does this relate to other consensus algorithms? This is not inherently a consensus algorithm in that sense. You can run whatever consensus algorithm you want in terms of the proof of stake mechanism. You can run a proof of authority where it's just one guy signing. The key design here is that designing around exits under a child chain construction, and how to reason about with block space availability when it comes to data availability, when it comes to ability to enforce fraud proofs, when it comes to being able to scale up from the ledger containing the memory state, and to be able to abstract that away into specific applications, and to be able to create decentralized applications whereby we're talking about potentially billions of transactions per second with incredibly low costs.
Okay, I'll take it.
Okay.
Great. Thanks, Joseph.
Okay,
This is really
thank
cool.
you. Sorry for going over.
That's all right.